Okay, thank you very much. Yeah, hello everybody. My name is Anna Ahlike from the Research Center in Jülich in Germany. And today I want to give you an introduction into track finding for the PANDA experiment. The PANDA experiment is a fixed target experiment located at the facility of antiproton and ion research in Darmstadt in Germany. And the experiment is still under construction. It will be operated at medium energies of 1.5 to 15 GeV/c beam momentum, and anti-proton beam will be collided with the proton target. As fixed target experiment, PANDA has a barrel part surrounding the interaction point and a forward part to detect the forward boosted tracks. In my PhD thesis, I focused on the barrel part. Here we have a solenoid field, and we have three different tracking detectors. The innermost tracking detector is the microvertex detector, which is a silicon strip and silicon pixel detector with a high spatial resolution to detect displaced vertices. PANDA's main tracking detector is the straw tube tracker, which is a drift chamber-based tracking system consisting of over 4,600 gas-filled drift tubes arranged in a dense packing. And the last tracking detector in the barrel part are the gas electron multiplier plates, which is a connection between the barrel part and the forward tracking system in PANDA, because they detect the forward boosted tracks in the barrel part. I already told you that the straw tube tracker in PANDA is the main tracking detector, therefore I want to give you here a few more details. The straw tube tracker consists of straw tubes. These you can see here in this picture, and here you can see the basic working principle I will shortly explain you. In green you see here a charged particle track, and if this charged particle track travels through the straw tube, it will ionize the gas in the tube, and the electrons will then travel to the anode wire in the middle of the tube. The drift time of these electrons can then be measured and result then in a circle around the center of the tube, which is called an isochron. And for track finding, it is important that the particle track is tangent to this isochron. And here in the on the left, you can see a three-dimensional picture of our straw tube tracker. Here you can see one segment. So the straw tube tracker consists of 6 segments. And here on the right, you see a projection of the detector in the XY plane. What we here in this projection can nicely see is that the detector consists of different regions. We have an inner region and an outer region, which consists of parallel tubes which are parallel to the beam axis. And in between, we have the so-called skewed layers. These are straw tubes which are slightly rotated by an angle of 3 degrees. And these skewed layers you can see here in this picture. What we also can see here is how a particle track looks like in our detector. We see that particle track will first go through the microvertex detector, then it will produce the isochrons in the STT. This you can here see as the small circles, and after that it will go through the gem plates. Okay, let me now come to the challenges we have to face in PANDA. I already told you that the straw tube tracker is our main tracking detector, so we have to include this isochron information into tracking algorithms. So usually a tracking algorithm uses 2-dimensional or 3-dimensional head points to perform a circle or a helix fit in a solenoid field. We in PANDA want to include this isochron information because it strongly improves our spatial resolution to 150 micrometers. An approach how we can include this isochron information is the so-called problem of Apollonius. This is a well-known mathematical problem that connects 3 circles with a 4th circle by being tangent to the other 3 circles. And here in this picture, you can nicely see that there won't be one solution, of course, but 2 solutions per isochrone. So for such a triplet of isochrones, we will get 8 possible solutions. Let me now come to the different tracking algorithms I want to introduce to you today. Today I want to show you 3 different tracking algorithms, where 2 of them are primary track finders. Yeah, so they can only find tracks originating from the primary vertex. And the last one is a secondary track finder, which can also find tracks coming from a displaced vertex. And for the secondary track finder, I will go a bit more into detail. Let me now start with the standard tracker. The standard tracker is the currently used track finder in PANDA. And it is, the benchmark. It was a benchmark for me in my PhD because I wanted to improve the standard tracker or develop algorithms which are better than the standard tracker. It has a quite simple procedure. It simply takes one hit after another and asks if this hit fits to an already existing track. If it won't fit to an already existing track, it is matched to the pool of it is filled in the pool of not matched hits. And with this pool of not matched hits, then new tracks are created by calculating circles from 3 hits. And in the end, the standard tracker has a cleanup procedure where small tracks are removed or tracks which were found several times. In my PhD thesis, I then developed another primary track finder, which is called the Huff track finder, and it is based on Huff transformations. So for a Huff transformation, I calculate all possible combinations of 2 hits and the interaction point, and calculate all possible Apollonius circles for each combination. The parameters of these Apollonius circles are then filled into such a 2-dimensional histogram, which is called a Huff space. The maximum in the Huff space then describes the actual track parameters. Let me now come to the secondary track finder. So I already told you for the secondary track finder, I want to go a bit more into detail. The basic idea of the secondary track finder is that I only need to find a well-chosen set of 3 hits, calculate the corresponding Apollonius circles, and I know that one of these circles must be my true particle track. Okay, now you can imagine that finding such a well-chosen set of 3 hits is already the most challenging part of the algorithm. So if I calculate too many combinations, my algorithm will get slow, and if I calculate too less combinations, the efficiency of the algorithm will drop because I can't find all tracks anymore. And therefore, I defined a set of inner SDT hits, a set of outer SDT hits, and a set of mid SDT hits, and calculated the combinations of these sets. To further reduce then the number of combinations, I force all tracks to be continuously in the SDT. And to further decide which one is the true particle track, I use then the number of hits in a track and the quadratic distance of hits to the circle. Okay, now when after I showed you the different track finders, I want to come to the comparison of the different track finders. And for this, I use a simulated data sample with 5,000 events. I already told you that we in PANDA want to investigate, we have medium energies, and therefore we want to investigate heavy hadrons like hyperons. In my PhD thesis, I focused on the cascade 8020 hyperon. And what is quite interesting for such hyperons is that they will decay into lambda particles. A lambda particle is a neutral particle with a quite long lifetime. So it is able to travel about 8 centimeters in our detector before it decays into the final state particles. And what I basically want to show you here is that we will get many secondary vertices, many secondary tracks in PANDA. Therefore, the secondary track finding is quite important for us in PANDA. For the results here, I show you the efficiency divided into primary tracks and secondary tracks, and also the number of wrongly found tracks and the number of tracks found several times. And the different track finder I compare here is the standard track finder, of course, as my benchmark, and then always a combination of the primary track finder and the secondary track finder. First the standard plus the secondary track finder, and then the HAF plus the secondary track finder. And what we see is, of course, the standard track finder alone is quite bad in finding secondaries, which makes sense because it is not the secondary track finder. When I then include or add the secondary track finder to the standard track finder, I was able to strongly improve here the efficiency for secondaries. With the HAF plus secondary track finder, I get even a better result for the secondaries. Now, of course, the final state efficiencies is not everything, and therefore I also applied it to a larger statistics with 400,000 events and wanted to perform a full event reconstruction. And here you can see the different combinations of the algorithms and the final state particle efficiencies. And in the last line, this is an interesting line for us, here you see the full event reconstruction rate. Now we see that for the standard track finder, we get a very bad full event reconstruction rate with only 2.4%. This makes sense because the standard track finder can't find the secondary tracks. When I add the secondary track finder to the standard track finder, I was able to increase this efficiency by a factor of 4. And with the HAF plus secondary track finder, I now get an efficiency of about 20% for the full event reconstruction. Yeah, with this, I'm already at the end of my talk. Today, I gave you an introduction to the PANDA experiment and the challenges we have to face. I showed you different track finders in PANDA, and I showed you that the secondaries are quite important for us. Adding the secondary track finder strongly improves our full event reconstruction. And furthermore, there are always things to do. So the next step is to optimize my algorithms for speed, because I want to make my algorithms online capable. At the moment, we don't have an online tracker in PANDA. For this, I want to calculate many events in parallel. Therefore, I want to use GPUs. I already started with this by porting the HAF track finder on a GPU. But here I ran into memory problems with the GPU, so I couldn't use the GPU efficiently. So here first have to find a better solution for this. And the next step will then be to see how the secondary track finder performs on a GPU. And this is everything. Thank you very much for your attention, and I will be happy to answer your questions.
Joanna. Questions on Zoom? Turn around. So Anna, can you define efficiencies for me, because I'm a little bit confused by what you mean by, well, I guess I know what you mean by full event efficiencies, reconstructing every single final particle, right?
Yeah, yes, it is not the final state particles, so the efficiency for the final state particles, I think this might be clear. This is how many final state particles I can get of all simulated, or I can find of all simulated final state particles. And the full event reconstruction rate is then how many full events I can reconstruct. So here also the momentum resolution is included, and I perform a vertex fit for the final state particles.
So your efficiency for when you in slide, what is it, 8, I think? Your full event efficiency includes reconstructing the primary vertex, the secondary vertex, everything.
Exactly, yes.
I see. Yeah, that explains it. And you don't have geometrical constraints. I mean, you want to reconstruct every single one of these 400,000 bits. Like there aren't region of the detectors in which you say I don't look there or things like that.
Yeah, so here I performed the full event reconstruction. So in my case, I only used algorithms which are able to find tracks in the barrel part, and therefore I didn't include an algorithm for the forward part of PANDA. Here I used the Monte Carlo data, an ideal tracking for the parts for the forward part.
Thanks, that's me. Marcus.
Yeah. Thanks, Anna, for this very interesting talk. I mean, I was a bit surprised that you're using Hopf transforms to reconstruct the Stroton pits into tracks. I mean, there are other conformal transforms, the Rondo transforms and so on, which typically people are using in these situations. Did you look at this?
Yeah, of course, I looked at this. So I also know that the Hopf transformation is not perfect because I saw it when I wanted to port it on a GPU. So the Hopf transformation is really not really good capable for a GPU, and therefore, of course, we are in the experiment, in the PANDA experiment, have several different approaches for track finding. Also, deep neural networks, for example. You will see in a second talk today. But in my PhD thesis, I had to look at the Hopf transformation, and because Hopf transformation didn't work so well, I then also had to look at the secondary track finder.
I mean, it looks like in your microvertex, at least by eye, on the event display on page 6, that one actually sees the tracks. So you could also think about doing some classical track seeding in the microvertex and then pick up the stores. No?
Yeah, I understand. The problem is that in a microvertex detector, we quite often can't find our secondary tracks because the secondary tracks are able to travel so far that they will decay here in the straw tube tracker. Therefore, we can't really use a microvertex detector hits for our secondary
tracking. That could work. No?
Yeah, sure. For the primary tracking, this can work. So, for example, the standard track finder, this uses the microvertex detector. I think not as seed, but yeah. So there it is used. Yes.
Okay. Let's thank Anna again.